everybody, welcome to the Spooky Action at a Distance television show. I'm your host, Kyle Finley, and this is the best show north, south, east, and west of the Rockies. And eventually I have to get a new intro phrase for that, but that's what we're sticking with. And today I have my guest over here, Dave Paris. How you doing, Dave?
Good. How you doing, Kyle?
Not fantabulous.
I'm fantabulous.
All right, yeah, we've always had Dave on here. You know, we always talk about a million different things. He's got knowledge in just about everything, so I love having him on here. And today we're going to be talking about space and, you know, kind of like where we're going, the general direction and whatnot. So what do you want to talk about first today, Dave?
Well, first we want to get a location of where we are in the Milky Way galaxy.
Well, we're right here. We're on Earth.
Yeah, we're on Earth.
Question solved. Let's move on.
But the galaxy is about 200,000 light years in diameter. And it's kind of the formation of it's kind of like a pizza pie with the center core of the Milky Way galaxy with black holes into the center.
Can we get some pepperonis on this pizza?
And you can get some pepperonis on that pizza. It's about 1,500 light years thick. And we exist onto the Orion, the spiral arm named Orion in the Milky Way galaxy. And where we're located on that spiral arm is approximately 30,000 light years out from the core, from the center of the Milky Way. So we would be classified as being located in the Goldilocks zone, which is, we have life here on this planet now.
Now, is that of the galaxy?
Of the Milky Way galaxy.
We're getting in the heavy topics here.
Well, I mean, that's where our location is approximately. And we're about 750 light years from the outer edges of the spiral arm. So the thickness...
750.
Yeah, in the thickness of the spiral arm, which is 1,500, we're approximately into the middle of that. So 750 either side. Light years.
Light years.
And we're talking light years, and so that's 6.8 trillion miles in a year. So it's not a trivial factor of light speed at 186,000 miles a second. So, and that goes on for a second, for a minute, for an hour, day, year, and that totality, when you add it all up, is 6.8 trillion miles.
Mm-hmm.
Well,
6.8 trillion miles. So
yeah,
we're not getting anywhere with chemical rockets.
Well, that's kind of hard to wrap your arms around. So we refer to it as a light year, as a relative distance. So within the local star group here, which is approximately, practically from about 500 light years in around the Earth area here, it's still a fantastic amount of distance. Alpha Centauri is 5 light years, Proxima Centauri is 4.26 light years away. And to get to any place outside of the solar system is going to require a special kind of technology and advanced concept propulsion, which we've talked about on previous shows about warp drive.
Yeah.
But
just for perspective, how long do you think it would take an average chemical rocket that we have today to do just 1 light year? You know, we're talking about moving multiple light years, you know, just for everybody.
How about if I give you an example of going to Alpha Centauri? It's 40,000 years.
40,000 years.
Yeah,
okay.
40,000 years, and you would be changing crews out. You know, one crew would, a generation would die off, another one would take over. I mean, we're talking 40,000 years, and that's
it's like all of human history.
It's impractical.
Yeah.
Okay. And so even within our own solar system, you know, Pluto's 3.8 billion miles away. And it took 10 years for the Project Horizon, a unmanned robotic craft, to reach Pluto from the Earth. That was 10 years at 50,000 miles an hour.
Yeah.
That's about it. So when we go to Mars, you're talking about approximately 10 months to get there. Now, there have been a lot of claims lately, Elon Musk with SpaceX saying that he could get there in a little over 70 days. Well, the chemical rockets are chemical rockets. It means you're going to push a lot of fuel up into space to then launch from the Earth to get into trans-Mars injection to get to Mars.
Yeah, and then you got to take all the supplies with you. You got to take a whole crew with you. You know, there's so
Well,
much stuff you got to take with you that just
Well, most
compounds
of
the
the
problem.
planning has been around the fact that in the southern pole of Mars is ice, and that you would then have to process and electrically separate the water into hydrogen and oxygen through electrolysis, and then manufacture your own fuel to get back.
Mm-hmm.
You know, something breaks, something doesn't go quite right, you're stuck on Mars.
Well, you got like potatoes, right? There was that potato farmer guy on that movie.
Well, and this is the whole thing. One of the reasons why you want to get out to space and create is what we're going to be talking about here through the program is a space-based economy. Now, if you know, we were all talking recently about jobs being at 3.8% unemployment, and the job market is filling up, and they can't get a lot of workers to fill the jobs and all this type of thing. And then everything goes into a cycle. Within maybe another 8 years or so, we may see another recession. And then you climb out of the recession and you go, well, if you have a space-based economy, you have an endless economy. There isn't any kind of low or high in the thing, because when you go to space, there's a huge demand on logistics. And that means, initially, is to get food, supplies to space. Right now, the cost of getting to space back into the 1980s was $30,000 a pound. That's why astronauts are small. They don't weigh much, and therefore they don't cost much to stick in this space.
They got to go on dives before they go up
Yeah,
there.
you don't want to send
We're
a guy.
saving every
You don't
buck
want to
here.
send a guy like me. I cost a fortune. You could send 2 people for for what I weigh.
Yeah.
But the cost of deploying and getting materials to space is rapidly going down. Now it's down into about the $10,000 mark, and I know like Elon Musk and SpaceX is trying to get it down into the $1,000 range. But I think with advanced propulsion techniques like the warp drive that we've talked about again, that we would get it down to just dollars a pound. And that would revolutionize not just the transportation of getting people, supplies to space, and manufacturing of goods and particular goods, high-tech goods that require zero G, like chips and silica cells and all this, solar cells and that. All that, once they're manufactured, can then be easily brought back to Earth.
Yeah.
Television screens, and I mean, there's just an endless array of electronic products that could be produced in space because of the zero G, which means less imperfections. That was really what the bottom line is. So will there be an advantage to go to space? Yes. Will there be an advantage to send humans to space? Well, initially, there's problems with sending humans to space. There's a degenerative process biologically with legs and extremities, and they have to exercise long periods of time in space, almost like 8 hours a day, and to keep muscles.
8 hours a day? That's like, that's quite a bit, you know, just for exercise. Like, is that what they actually do right now, like on the International Space Station?
Yeah, there's they have these regiments of different kinds of exercises, and you know, I'm not clear as to if it's every other day or something like this, but there's a tremendous amount of exercising that you have to do in space to maintain the extremities of the body. Now, one of the proposals that we've had on our warp drive is the smaller renditions of those is to actually create artificial gravity. That will be a key working in space. It's tough enough to be out there and being exposed to radiation, cosmic rays from outside of the solar system, cosmic rays from the sun, radiation from the sun, ultraviolet, all these types of things.
All kinds of problems.
And then you got meteorites and small pieces and parts of satellites and craft that have during separation have explosive bolts have thrown shards of materials out into space. And we're getting to a point where we almost won't be able to leave the Earth because there's so much. NORAD has tracked like, there's like 60,000 tiny pieces left, less than a ½ inch, that they're tracking in space. I mean,
Yeah.
the place is loaded with junk. So we're gonna have to figure out some way to clear that out.
But the first thing with the artificial gravity, we kind of got like a solution for it.
Correct.
We got a picture of it. Jake gets it on there. There you go. You found it.
Yeah, what we would do is using a smaller version of our larger motors, is put them under the floorboards of the spacecraft and energize them maybe to less than 100 watts of power. And the pulling power of the motors would then effectively put artificial gravity inside the craft, and people then could walk around. And it would save them from having to exercise exorbitant amount of hours during the day to keep everything trimmed and muscles taut and everything like that.
Of course, if you just get used to space, right? Couldn't we just have people, if they lived their entire life in space, they wouldn't need to worry about that, right?
Well, you know, as they deploy to space right now, and if they go up greater than just a few months, when they come back, they have to be carried out of the spacecraft on a stretcher.
When they come back. But if they just stayed in space.
But if they ever did come back, it would be real critical. Their lungs would not be as strong. Their physical body would not be as strong. It takes days to recover coming back from space. I don't think a lot of people realize that. That's why it's imperative that new methodologies and techniques like we're suggesting here with artificial gravity be employed to go to space. Otherwise, you stand a risk of deterioration of the body, which is not a good thing. And particularly if you're trying to then exploit space, like go to the asteroid belt and do mining for gold, silver, platinum. I could make a comment here that platinum is in a crucial piece of element that we have to have here on Earth. We don't have enough of it. You can't be an advanced society without large quantities of platinum. And platinum is freely available into the asteroid belt.
So once we get out there, we can get abundant amounts of platinum and then just throw that into the economy, and then technology
because that's
can
all
take off.
catalytic converters, for example. You want to clean the air? Well, you got to put platinum in there.
I don't want to clean the air.
You don't want to clean it?
Give me the smoggy pollution stuff.
But to produce fertilizers and things for agriculture, you got to have platinum. To do semiconductors, you got to have platinum. So all of these different processes that we have for you know, a technologically advanced society all require basic needs for these raw elements of platinum. Gold and silver obviously is needed in also the manufacturing processes for electronics. I think everybody's pretty well aware of that.
And
but
for coinage, right? We got to have gold.
Well, and coinage, sure. You got, you know, William Devine, he sells gold all the time on television. But bottom line here is that as we look at space initially as a mechanism to begin the space-based economy and to become a spacefaring nation. Now think of all the skill sets that you have to go to space. So you got to have engineers and scientists, programmers, electronics manufacturing, aerospace companies. They got to build the craft. Everything has to be put together, assembled, kind of like jetliners and stuff. There's a huge marketplace, billions and billions.
You're going to need social workers to keep everybody sane out there.
Well, then you're going to have space stations, and if they have artificial gravity, then you're going to have a staging area to go from the station to other parts within the solar system.
You need cooks to make food. Well,
Oh, yeah.
Maybe not. They'll just have the prepackaged stuff.
Well, initially, you're going to have that. But as everything evolves and begins to get structured and more expansion in the manufacturing of craft and getting all the skilled set people in place, now you have this huge economic base of people with salaries, getting money, upping their status, middle class and upper middle class and all this type of thing.
It's going to be space-based class.
And it's going to, well, but the
They're in their own class.
The thing is, I believe that the global economy is not really one that is going to be enough to sustain 7.5 billion people on the Earth.
Yeah.
I think a space-based economy is going to allow a much broader expanse of technical skills and bringing up a lot more people into that realm. Because once you're in space and you start to colonize a planet, like say even like the moon, for example, if you colonize the moon, well, initially there's a lot of dependence on the logistics that go to the moon. and you got to supply the food and all the materials initially. But once you get to the moon, you can manufacture your own building blocks of the materials, the silica-based materials.
And
that are on
that'd
it.
be a lot cheaper than bringing all that stuff along with.
Yes,
so
but you got to bring the initial devices,
machines and
the
stuff
machines
with
and stuff to build the blocks, heat them to the proper temperature, and fuse them together, and all that type of thing.
We should have an artist diagram of moon base. That's not it, but we'll get it.
But
it's from NASA, but yeah, it kind of shows, and I know you wanted to talk a little bit about the lava tubes being
it's a natural formation on the moon, and these things
There's the picture.
are many feet thick as a result of the magma or the lava that comes out of the moon-based volcanoes. Now they're very flat, and because of the 1/6 gravity, they lay very flat, even the volcano itself. But the lava tubes are extremely thick, and you need at least 4 feet of materials in order for the radiation to use it as a block for the radiation. So these tubes can be as much as 6 and 10 feet thick. And so if you penetrated the side, there would be a hole inside the tube, and then you could erect buildings and whatnot. So you would have additional protection from meteorites striking the moon, because you don't have an atmosphere, they don't burn up.
Yeah.
So there's other hazards that have to be worked out and engineered.
Now, would those lava tubes be airtight? Would they be able to, just like make an entrance hole and then just...
No, well, they wouldn't be airtight. They would just, you would go into them and then have structures within the lava tube.
Kind of like
itself.
the Bigelow space hotel thing, where you just like inflate a thing.
Probably when you can manufacture your own building blocks from the lunar materials, then you would just build buildings from that in there, and then fabricate inside, and
Like an igloo or something, huh?
or whatever. But then those buildings would then have to be airtight, because obviously there's no atmosphere. So there's a lot of problems initially that have to be worked out. They're solvable. I mean, we actually have lived in space. The International Space Station is a good example. I mean, there's not very many people, 3 or 4 at a time. It's built for 7, but it's a small segment of the population.
Yeah.
But the more you learn from the biomechanics of the whole of conducting living experiences in space, then you can offshoot from there and work those into the traveling spacecraft for mining, because that's what initially is going to get people to space, is the wealth that's out there, like helium-3 for fusion reactors. The moon is penetrated with, on the surface, of helium-3 that comes from the sun.
Yeah, I know you often talk about, I don't know if we talked about it before, but is that just like the surface dust on the moon? Is that
No,
helium-3,
it's actually an element, helium-3. It's impregnated into the soils. It comes from the corpuscular material from the sun.
Corpuscular? Can we use that? I don't think we can use that on the TV.
Well, look it up.
Corpuscular.
Corpuscular, atomic materials, pieces and parts.
Okay.
As it comes through across the heliosphere from the solar wind, and that impregnates into the lunar soil. So there's huge quantities. We have billions of years worth of this stuff that is into the soil, and all you have to do is heat it up to get it out. You dig it down, you dig the surface materials, process it, and then actually extract the gas that's there, the helium-3.
And then that's used as a energy source, right? You can put that into like something and you get energy out of it?
Yeah, actually in a fusion reactor, if you use helium-3 as part of your fuel versus deuterium, now we could extract deuterium from ocean waters, for example, and use 1% of the ocean water, extract deuterium, and we could get 500,000 years of power from 1% of the ocean water using deuterium. But that's a low-powered fusion reactor, and that's like 3.2 million electron volts per fusion reaction of the deuterium bumping into each other in a proper containment system.
Yeah. Do we have any current day fusion reactors that would be able to process that thing?
Well, unfortunately, the reactors that we have only been able to attain about 17 microseconds of power.
17 microseconds.
Yeah.
That's not very long.
It's not. No. It's not really good. And they've been working on this for like well over 30 years. And they're thinking another maybe 25 years they're going to perfect this. The Tomac reactor, which is in Russian is the term new energy source. The fusion reactor would be the main power supply that we would take to space, because it's really, it doesn't interact with humans in the sense of radiation output is benign to humans. And if it does breach its containment system, it just fizzles out.
So a lot safer than like a nuclear reactor.
A fission reactor is extremely hazardous. Now, it can be contained with the proper engineering and science that goes into all that. And they have been maintained for well over 40 years in this country. And that could be the new energy source for us. But fusion has always been on to the horizon of being the type of energy source that we could take anywhere we wanted. But that's what we would use to go to space. That's what we use to colonize the moon or Mars or other places. It would be a practical thing because the materials that are needed to fuel them are plentiful all over the place. All you got to do is extract them out of the surface. So from that standpoint. Now the other thing is the practicality of the spacecraft. Now a lot of these privatizations of space, of SpaceX, Burt Rutan and his company that he recently sold to Northrop Grumman, that put Spaceship One into space for 64 miles, and that was the limit to what they were able to do.
What were they trying to accomplish? Would they just like throw it out there?
You know, they're going to take passengers. This is for tourism. This is to try to get the start of getting space exciting. Bigelow Aerospace was the habitat shelters.
Yeah.
They're inflatable Kevlar containment systems, living quarters. They're not real fancy, okay? They're real basic stuff. It's basically a inflatable, has some decks on it and stuff. Yeah. But he's looking at creating space hotels.
One of those kind of experimentally set up for the ISS. I think they just kind of like had it on one of the branches.
Yes, and that was another thing to try to expand and see about the construction and how easy it was to fabricate and put these things together. So it's coming. Are we going to see a lot of this in our own lifetimes here?
Oh, maybe in my lifetime.
Well, maybe in your lifetime.
I'm not saying anything, Dave.
I'm hoping that I see it in my lifetime. I hope by the fact that we're building this motor will get us out there a lot quicker than this World War II type technology chemical technology that we're using, because ion drive just doesn't have it. It really is inefficient, and it uses less fuel, granted, but it takes an awful long time to get from point A to B. And that's what the whole crux of this thing is. In order to really evolve a space-based economy, you have to have an efficient mode of transportation. You have to have efficient engine technology that will get you from point A to B in a short period of time. Now, we've talked about on the program in the past of 45 days to get to Mars with just how our engine sits right today. Now, we have advanced motors that we're testing here actually next week. And hopefully the outcome of that is that it will be double the power and all this type of thing. So we'll be getting closer and closer to perfecting the motor from a standpoint of literally influencing and getting materials and people into space, from Earth to space. You know, you have to remember is that the rocket technologies that we have, 90% of the weight of the rocket is fuel. You only have 10% for the payload. Now, the further you get to the equator, you got about another 13 miles of girth on the Earth that it doesn't require as much fuel to get to space. But you also have to remember, space starts at 50 miles, but can you do a suborbital flight at 50? No. You got to get up to 103 nautical miles in space in order to actually achieve a suborbital process.
I'm sure all us laymen will write that down and keep that in our books.
Well, it's a number that strikes me as being, you know, that's the critical point. If you go below that, you burn up.
Yeah.
Unless you have power to boost yourself back out. So it's an interesting crux of problems. I think we've solved many of the, to become acclimated into space with spacesuits, food and materials, and we've shown that people can go, like Russians have put up astronauts for 1.5 years in space.
Yeah.
So we know that a human can live in a zero-G environment for extended period of time. But again, you know, it comes with a penalty. And what we're talking about today is to become that spacefaring nation, you have to solve these other problems, which I believe we have answers for.
Yeah, it sounds like you got a lot of problems solved just here with the technologies we were talking about. Like one for the artificial gravity.
That's key.
Another one for
the warp technology to get stuff from the Earth to space for a couple of dollars a pound.
Yeah, much cheaper. And then the shield. We didn't really talk about shielding, but I know that was in there.
Shielding is another aspect of it. If you're going to go a long time in space, you're going to be subjected to cosmic rays and X-rays and all types of high energy sources. And the thing with the creating a field around the spacecraft is to emulate what occurs around the Earth with a magnetosphere. So you would create a magnetic field up and around the spacecraft in addition to the warp bubble and everything else. But this would prevent radiation and everything.
That's all you get for that one. So we got shielding, we're wrapping up the program here. So you got artificial gravity, transportation, shielding, and then energy with the fusion reactor. You know, all this stuff needs to be worked on and developed.
Right.
Coming to the end of our show, so I want to thank our audience for joining us. Anybody in MUFON, check out the MUFON Journal article that has been published.
Go to the website, read our paper.
Go to the website, read our paper, and follow us on YouTube and Facebook. See you next week.